So we come to the explanation of the Navier Stokes equations. Before we start the explanation, we want to make a short summary of all the conservation equations we have to solve. If you use under CFX, we have to solve at least 6 equations. We have to solve the mass balance, the so-called continuity equation. And we have to solve the Navier Stokes equations, and we have to solve it 3 times. We have to solve Navier Stokes equation in x direction. The velocity, it's a more or less momentum balance. The momentum balance in the x component is also always described with the symbol U. The momentum balance in the y direction has a symbol V, and the Navier Stokes equations for the z component is described with the symbol W. Additionally to this 4 equations, we have to solve 2 other equations for the description of turbulence effects of swirls. Therefore, we also use a model. We use a conservation equation for the turbulent kinetic energy K, and for the dissipation of the swirls, the dissipation of the turbulent kinetic energy. And therefore we use the symbol epsilon. Okay, now we have to look closely at the equations. At first, you all have done successfully your simulations. You know the so-called solver manager in CFX. And if you open the solver manager, and if your simulation runs without any problem, you don't look at this log file, but you know if you have a crash, if something did not work so well, you have to look at your log file and you have to see where the problem occurs. And in your log file, if you look closely at your log file, you have to read it, and I think you have to understand it. Here you have the iterations. Here we have the iteration 8. And here you see a hint for the equations that were solved. We have UMOM means velocity in momentum in x direction. VMOM means momentum in y direction, and WMOM means momentum in z direction. P mass is the mass balance, and if these equations are solved in a proper way, if they converge, we get a big OK here at the end. And if you remember your homework, your simulation tasks, this here you see the residuals of your run, and this is the red line is the residual of the mass balance, and this blue, green, yellow lines, they are the residuals for the Navier Stokes equations. So if your simulation runs in a good way, they go up, and then the residuals go down if you have higher numbers of iterations. And that's always something you have to check. If this line goes upwards, your equations are not solved. Then the equations did not converge, and then you can't take this result as a real. Okay. Let's look at the first equation, the mass balance. I sketched a simple cell. That's only one cell where you calculate the mass, and mass comes in. Here we have rho density times velocity times the area. dy times dz is the area. So rho times u times area is a mass flow. And not all the mass comes out or goes in here at the side. some of the mass will go to the other way in another direction. So you have to solve this balance additional to this diffusion coefficient. Yeah? Then we can simulate. So you see more or less for the mass balance and one cell, you need 1, 2, 3, 4, 5, 6 different equations to calculate how much mass we have inside the cell and how much mass goes outside the cell. Okay, I think this is at least not so easy to understand. And it's just the first equation. Now I told you in science, we always have, or from time to time, we have conflicts between scientists. And here we had the conflict of Mr. Navier and Mr. Stokes. Here, one is missing. Yeah, of course, he didn't live so long. Yeah. But in this case, I told you about the conflict of Isaac Newton and Mr. Leibniz, or about the conflict of Euler and Lagrange. But in this case, we found a combination of both descriptions. We found a combination of Mr. Navier and Mr. Stokes. And so we call the equations today the so-called Navier Stokes equations. And they are solved in ANSYS. And you can see how good they are solved. You can see it in this solver monitor, in this solver manager. Okay. Now, how is the formulation of the Navier Stokes equations? And I know this equation looks really terrible. It's a long equation. And the students always say, oh, it's too complicated. But I think if we look closely and try to understand it, it's more or less not so difficult. Yeah, this first formulation of the Navier-Stokes equation in x direction describes my velocity u. So it only describes one velocity. And you can imagine the other velocities, the description will just be the same. Yeah, just copy it. Okay, but first we concentrate on u velocity. And first we have the so-called dynamic term. We have du derived by the time. Yeah? This first term describes the derivation of my velocity over time. So it describes how much will the velocity change after 1 second, after 2 seconds, and so on. And you can imagine if you imagine fluid flow, a water pond, you swirl a bit around in the water, and after some minutes, the velocity disappears. It just disappears. Okay. Second term is a convective term, so-called convective term. It describes how your velocity u will change over the different distances. Yeah, if you come here, you come inside with maybe 1 meter per second, and after, let's say 1 centimeter, this velocity changes, for example, to 0.7 meter per second. So your velocity gets smaller over this way. So this is described by this derivation, but the velocity u will also exit at the sides of this box. Yeah, so you should also describe it in the other directions. You have to make the derivation. Okay. Then additionally, term has to be taken into account, the so-called diffusive term. And diffusivity, yeah, it's not the same movement as convection. Convection just is normal movement, but diffusion is, yeah, the movement to the sides, more or less. Yeah, and here you see the viscosity is added to the diffusive term, And this term describes you, yeah, how viscous your media is. For example, if we have water, it's not so viscous. Yeah, the viscosity is not so high if you have water, and then your viscosity, your velocity can be transported here through this box. Really simple. But if you have a thicker medium, for example, honey or mud or so, with a high viscosity or tar, then the diffusive terms will be much higher and the movement will be more to the sides of the boxes. Okay, I will explain this diffusive term a bit more in detail later. And additionally, just remember your Bernoulli equation. Now we have also the gravity term. Yeah, it's the same as in Bernoulli. And we have a pressure difference. Yeah, derivation of the pressure after the x component. Okay, that's more or less the description. And this is a description for incompressible flow. So if the density does not change, you can imagine if we have compressible flow, it can be a bit more complicated. Okay, I changed the slide, mention it. Now we have the third Navier Stokes equation, the green one, and the slide is nearly the same. Yeah, it describes the movement in v direction, and we describe here this movement in the y direction, and it looks pretty much the same as the slide before. And with the w direction, it's the same. It also looks pretty much the same. I just changed this w here. And that's something that makes it also a bit more easy. If you imagine you must program this, for example, if I give you the task, you should, for example, write a software code, write a program, and you have to program this equation. The program will always look similar. You just change the component, the velocity component. So the code will be every direction the same. Okay. So here again is the same description of convection of the u velocity. You have a big part in u direction, but you add something from w direction. You have to add a u component from w. It comes from the cell below, and so your derivation can also be bigger than the momentum that entered here. Okay. And if you look at diffusion, you can also lose momentum. Yeah, if velocity enters here, for example, 2 meters per second are entering here, then you have a high viscosity, and some of the momentum goes to the side. Yeah, not all the momentum exits the cell here in the x direction. Some of the momentum can exit can exit this cell in x direction. And this can be mathematically really good described by so-called second derivation. That is a second derivation of the velocity describes the diffusivity. Okay, this is, I think it's quite tough, and it's, now you ask me, why do I need viscosity? It's so complicated. Why do I need to describe diffusivity? It's convective term is much more easy to describe, but the secret is viscosity really much influences our efficiency. And if you remember your homework, the wing, for example, if you make a CFD model of the wing, and the best thing to get a high lift, you take a high angle of attack. Yeah? But there comes a point where physics will not help you anymore. Yeah? If you make the angle of attack too high, you get a stall effect. So if you have a stall effect, you will not have any lift off anymore. The whole force, the whole lift force will go down. So, and this is in many technical applications the same. Yeah, viscosity really much influences the efficiency. Yeah, if we have a broad range of viscosity and efficiency, at first efficiency is not really high. Yeah, for example, if viscosity is really low, your wing is not really efficient. But if you get a higher viscosity, your wing gets much more efficient. For example, if you take the example of a submarine, they also have wings, and the wing of a submarine is much more efficient than the wing of an airplane, yeah, because the viscosity of the fluid is higher. But the mechanical efficiency will go down if you have higher viscosities. Take, for example, a gear, yeah, a gear of a car. If you have really high viscous oils in your gear, efficiency goes downwards. Okay, that's the secret. And you're an industrial engineer. You want to be industrial engineers, masters, and you always have to build machines that are really efficient. Yeah? If you want to build a gear for a car that is efficient, or you want to build a wing for an airplane that is efficient, you have to take the viscosity into account. Yeah? Otherwise, you can't calculate efficiency. Yeah? That's a bit the secret of the viscosity. Why do we need it? Yeah? For example, if you calculate a pipeline with Bernoulli's law, you can never tell a lot about efficiency because you don't take the viscosity of the fluid into account. Okay, what is now viscosity? Viscosity, I showed you this experiment with these two iron balls. They were dropped into this liquid. It's an oil, it's a motor oil, two different motor oils, and one is more viscous, the other one is less viscous. And if you refer to YouTube, I made this movie for you. You can turn around this pipe. I don't want to click the link now because it's not good if I click a link from one YouTube video in another. Sometimes I get some crash with my computer if I do it. So I don't want to do it now. You can do it on your own. There you can see video where you turn around these two pipes, and then you can see that one ball is moving faster and one ball is moving slower. And this is exactly described by the so-called shear viscosity. Shear viscosity can be calculated by derivation of the viscosity times density times lambda divided by 3. Okay, so let's summarize the momentum. You have seen the momentum equations for incompressible fluids and explained you that this phenomenon was first described by Mr. Newton, but it was described by the Navier Stokes equation by the scientists Navier and Stokes. That's also a thing I want to mention here. And that is also, again, important if you want to enter some values to answers. We have a so-called dynamic viscosity and we have a kinematic viscosity. And the dynamic viscosity with the symbol eta has the unit Newton times second divided by square meter. And the so-called kinematic viscosity is the dynamic viscosity divided by density, and then we get the unit square meter per second. And please take care, be careful. The values of these different viscosities has a really big difference. Yeah? It can be a factor of 1,000 different value, and a problem. Sometimes the students have a problem if they have to enter the viscosity by their own into ANSYS. Then I tell them, oh, make a simulation with water, for example, and what are this, or with the oil, make a simulation with a motor oil, for example, and then the students start to Google. They look for a viscosity, and then they take the wrong viscosity. And if you enter the wrong viscosity into ANSYS, you get totally different values. So please take care, always take the right viscosity as a input value. Okay, that's something we have to, I have to show you in ANSYS where you can find this, this field where you enter the viscosity. Okay, so we have dynamic and kinematic viscosities, and we have different, of course, they are different for gases or for liquids, and they also depend on temperature. So if you have a gas and you have a higher temperature, the gas gets somehow thicker, so the viscosity rises. For example, if you're in a fire or in a hot temperature, viscosity of the gas is really higher. And if we have a liquid, oil or water, it's just vice versa. If you make oil hotter, it gets more liquid, so it gets a lower viscosity. Okay, so this depends on molecular movement. If we have a gas and the molecules move faster, we get higher viscosities. If we have a liquid and the molecules move faster, we get lower viscosity. And this viscosity influences also the diffusion movement. Yeah, here's a short summary of this. I'm sorry, it's more or less in German language. I have to translate it in the future. If we have here this, if we have gases, Newtonian gases, the derivation of our viscosity, of our velocity, so is if you make it higher, so if you have more shear, if you can imagine you have, for example, here a plate, you put some oil on it and a sheet of glass over this oil drop, and then you take a force on this glass, you shear it a bit, and then you have higher shear forces in liquids and lower shear forces in gases. I think you know this behavior also from real life. Okay, so, and last but not least, we have to look on the forces. That's also something you must know. If you remember your wing, you want to calculate the pressure field on your wing, you want to calculate the forces, the drag force or the lift force, and you can solve here this is your different shear stresses, and the shear stresses added to the force is the derivation of the velocity. So more or less, I summarize, you need the viscosity to calculate the forces on the walls. If you want to if a fluid goes over a wall, over the wing, for example, with a defined velocity, and then you need the viscosity to calculate the forces on the wall. Okay, and you don't have to do it on a sheet of paper. The computer is doing this calculation for you. So I think you must not solve it by yourself. The computer will solve it. So I just have to inform you about this, that you get a bit of understanding about it. And yeah, then Ansys will do it for you. Okay. Yeah, this is again the same. And here again is the shear. If you have your fluid volume, here the wall, you have fluid volume and you have shear forces. Yeah, you have tensions on the fluid, and then you can calculate how much these tensions are. If you have the movement, yeah, you have the velocity. Maybe this is an oil droplet. It looks rectangular, but let's say it's a droplet. And you have your glass, you have a plate on the top, and you move the plate with a defined velocity, and then you get your friction inside the fluid. You need the viscosity to calculate it. Okay, this is the same. Yeah, that's also a stress, normal stress. You also need the viscosity and the gradient of the velocity to calculate the normal stress. But additionally, here you have to add the pressure. You know, pressure is also the force on the area. So to your normal stresses, there will be added a pressure term. If you have a high pressure in your gas or in your oil, this causes stresses inside the body of your airplane. Okay, that's a lot of theory, but finally we get it. Now we have explained the whole Navier Stokes equations. You've seen it's tough work to understand it, to understand why you need it. You need it to calculate forces in the right way. You need it to take into account viscosity, viscous effects, to calculate different fluids. If you maybe, for example, want to design a gear of a car and you want to make the calculations for two different oils, you have to take into account the viscosity of the oil. Okay, that's it, more or less. So I would say, Mr. Martin, stop the movie.